Now we will move on to curve sketching. So we will start with a basic curve which we will try to graph together, and then I will give you a general strategy of how to sketch curves, and then we will try another example. So our first example is from page 304 in the book. We will graph together y equals to e to the power of 1 over x. So one thing we might want to start with is finding the domain. So note that if we have e to the power of x, the domain is all reals. However, if we have e to the power of 1 over x, note that in the exponent we have 1 over x, so x is in the denominator, so x cannot be 0. So the domain of the entire function is all reals except 0, so we can write it with intervals negative infinity till 0 and open bracket at 0 because we do not want to include 0, union 0 till infinity. This is our domain. Now that we found our domain, we can move on to vertical asymptotes. So our potential vertical asymptotes are any points that do not belong to the domain. So in our case, the point that does not belong to the domain is x equals to 0. So this is a potential vertical asymptote. So we would like to know how the graph behaves as we approach 0 from the left and from the right. So the limit as x approaches 0 from the right, so this is a reminder that as we approach 0 from the right, 1 over x approaches infinity because 1 over 0 from the right approaches infinity. So e to the power of 1 over x approaches e to the power of infinity. Again, let's look at the graph. It will keep on increasing, so it approaches infinity. So the answer of the limit is infinity. Therefore, we have a vertical asymptote when x equals to 0. Now, we do know that we have a vertical asymptote, but it's still important to check how the graph behaves when we approach 0 from the left. So when we approach 0 from the left, 1 over x approaches negative infinity. So e to the power of 1 over x, we want to look at e to the power of negative infinity. We can see here that the graph will keep on decreasing and will be almost, so it approaches 0. So from the left, the graph approaches 0. So this is what we're going to do regarding vertical asymptotes. And now let's move on to horizontal asymptotes. So let's find how the graph behaves at positive and negative infinity. So as x approaches infinity, we said that 1 over x, so let's write this down, x approaches infinity. So 1 over x approaches 0. So the limit as x approaches infinity of e to the power of 0 is the limit as x approaches infinity of e to the power of 0 is 1, and the limit of a constant is the constant. So we have a horizontal asymptote at y equals to 1. Now let's look as we approach negative infinity. So as x approaches negative infinity, again 1 over x, so 1 over negative infinity approaches 0. So this is the limit as x approaches negative infinity of 1, which is 1. So both of these two limits show us that we have a horizontal asymptote at y equals to 1. Now let us apply the knowledge we just learned earlier before about derivatives in order to find when the graph is increasing or decreasing. So let's find the first derivative. So keep in mind that our function is f of x equals to 1 over x. So the first derivative equals to first the derivative of 1 over x, and then we multiply it by the derivative of 1 over x. So the derivative of e to the power of 1 over x multiplied by the derivative of 1 over x, which is equal to e to the power of 1 over x times negative 1 over x squared, which we can write as negative e to the power of 1 over x divided by x squared. So when is it increasing, decreasing? So we said if the first derivative is greater than 0, then it is increasing. If the first derivative is less than 0, then the graph is decreasing. Now, when is the first derivative greater than 0? When is it less than 0? So let's find out. So, just to point out that our first derivative, x squared, is always positive. And e to the 1 over x is also always positive. So, our derivative is always negative because we have this negative sign here. So in this case, when it's really simple to know whether it's positive or negative, there's no need to really draw a sign table. If it helps you, of course, go ahead and do it. But now that it is clear whether the derivative is positive or negative, we will just use this fact. So the first derivative is less than 0 on the entire graph. The entire graph goes from negative infinity to 0 up to 0 to infinity. So on these intervals, so on the entire graph, f is decreasing. So again, this is how we know whether the graph is increasing or decreasing. Now, if you were to try to find any critical numbers, so you set the first derivative to be equal to 0. So we would like the numerator, so in a fraction, if you want something to be 0, it's always the numerator that's going to be equal to 0. And you notice that the exponential function never touches 0. So this is never 0 or never true. So no critical numbers. And now let us move on to the second derivative. So f prime prime of x. Again, let's look at the first derivative. It's a fraction. So we do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And keep in mind that there's a minus sign outside of everything because we have a minus sign in front of e to the power of 1 over x. All of this divided by the denominator squared. So if we were to simplify this, let's go ahead and do it. So this gives us x squared e to the 1 over x divided by x squared, and this is negative, minus 2x e to the 1 over x, all divided by x power 4. Let's distribute the negative sign, so we get x squared e to the 1 over x divided by x squared plus 2x e to the 1 over x divided by x power 4. X squared and x squared cancel out. So we get e to the power of 1 over x plus 2x e to the power of 1 over x divided by x power 4. Now we can factor any common factors. So we factor out e to the 1 over x. We get 1 plus 2x divided by x power 4. And this is our simplified second derivative. So now we would like to find the inflection points. Let's try and solve each term in this second derivative equal to 0. So let's try and find e to the 1 over x equals to 0. 1 plus 2x equals to 0, x power 4 equals to 0. E to the power of 1 over x is never 0, because the exponential function never touches 0. Now 1 plus 2x, we solve it, so x becomes negative half, and for x power 4 equals to 0, x equals to 0. Based on that, we can now draw our sign table. So e to the power of 1 over x is always positive. 2x plus 1 is 0 at x equals to negative half, positive above it and negative below it. X power 4 will always be greater than 0, and it will be 0 if x equals to 0, but 0 is not, in fact, in the domain. Now the second derivative is negative, positive, positive. So we have downwards concavity, upwards, upwards. We can write this downwards concavity from negative infinity to negative half, and upwards concavity negative half till 0 union 0 till infinity. So again, when the concavity changes as we have here, this means we have an inflection point. So x equals to negative half is an inflection point. Let's find its coordinates. So negative half and e to the power of 1 over x. So e to the power of 1 divided by negative half, so e to the power of negative 2. These are the coordinates of the inflection points. Now it is time to actually sketch the curve. So let us do so. First of all, just draw the y and the x axes. And then you can sketch the asymptotes. So we said we have a horizontal asymptote at y equals to 1. And regarding vertical asymptotes, let's check what we wrote. We said that when we approach 0 from the right, the graph approaches infinity. However, when we approach 0 from the left, the graph approaches 0. So let's sketch this somewhere on the graph. So when we approach 0 from the right, we are approaching infinity. So we have a vertical asymptote at 0. So this is just an earlier version of the sketch. As we add things to it, it will get clearer how it's supposed to look. However, as we approach 0 from the left, the graph approaches 0. Just remember that 0 is not in the domain. So here, let me. Okay, so here it's an empty dot. Now, let's look at concavity and when the graph is increasing or decreasing. So we said the graph is always decreasing. So let's look at concavity. If the graph is decreasing and we have this downward concavity, so the part of the graph that interests us is this second part of the concavity. So from negative infinity till negative half, we have this second part of the downward concavity. And from negative infinity till 0, we have this first part. So basically we have something that will look like this. And this would be our inflection point. So maybe let us graph our inflection point and base ourselves from it. Our inflection point is at negative half. So if this is negative 1, then this would be negative half. And the coordinates are negative half and e to the power of negative 2. So we can plug in e to the power of negative 2 on the calculator to see what value it gives. It will give something around 0.1135. So maybe it'll be something like here. So this is our inflection point. So I will maybe write negative half here to avoid taking up space. So again, we said that we will have something that goes like this, inflection, and then like this. So we can attempt at graphing it. So we have something that goes like this. We have the inflection point, and then something like this. One thing to keep in mind, this is an asymptote, so the graph keeps on approaching it, but never in fact touches it. So now we got how our graph looks from the left. So now let's look at how it looks right here from the right. Since we know that we have an asymptote here and another asymptote here, let's check the concavity to make sure what our graph is supposed to look like So let's check the concavity from x equals to 0 till infinity. So if the graph is decreasing, then we have this first part of the upward concave. So our graph will look like this. And this is how the graph of e to the power of 1 over x would look like. So the following are the techniques or strategy of how to sketch a curve. So first of all, we start by finding the domain, and then we find the x and the y intercepts. Then we find the horizontal and the vertical asymptotes. Then we find the first derivative, use it to know when the graph is increasing or decreasing. We can also use it to find the critical points, and it can also be helpful to find local minimums and maximums. And then we find the second derivative, we use it to identify concavity and inflection points. And then we can sketch the curve. So let us apply this strategy in an example. This example is from page 322 in the book, and we will be graphing the curve y equals to 2x squared divided by x squared minus 1. And I will be giving you the first and the second derivative. So the first derivative is negative 4x divided by x squared minus 1 all squared. And the second derivative is 12x squared plus 4 divided by x squared minus 1 all cubed. So let us start by finding the domain. So this is step 1, domain. So 1, domain. So this is our curve 2x squared divided by x squared minus 1. We can simplify the denominator and get x minus 1, x plus 1. So where does this curve not exist? Are there any conditions on it? So you can notice that the numerator is okay, it can exist for all real numbers. However, the denominator should be different than 0. So x minus 1 times x plus 1 should not be 0. So x minus 1 should not be 0, and x plus 1 should not be 0. Therefore, x is different than 1, and x is different than negative 1. So the domain is equal to, let us write this with intervals, negative infinity till negative 1, of course open parentheses because we do not include negative 1, union negative 1 till 1, union 1 till infinity. So this is the domain. Now let's move on to what was here, intercepts. So for intercepts, let's start with the y-intercept. So when x equals to 0, let's see y equals to 2 times 0 squared divided by 0 squared minus 1, which is equal to 0. Therefore, this is our intercept 0, 0. This is both the x-intercept and the y-intercept because both x and y are 0. And we will now move on to asymptotes. So we will start with vertical asymptotes. So our potential vertical asymptotes are the points that do not belong to our domain, so -1 and 1. So we will check the limits as we approach -1 and 1 from both the left and the right. So let's start as we approach -1 from the left. Keep in mind that as we approach -1 from the left, this is as if you have a value that's maybe like -1.00000 and then 1. So if you were to square it, so if you were to square -1.0000001, you will get a value that's positive and that's slightly greater than 1. So you will get 1 from the right. So a value that's slightly greater than 1 minus 1, this will give you 0 from the right. So the limit will give us 2 divided by 0 from the right, which is positive infinity. Now, as we approach -1 from the right, this is a value such as -0.9999999. So this will give us 2 divided by 0 from the left, which is negative infinity. Now, as we approach 1 from the left, this is as if we have 0.99999. So if we square it, we also have a value still slightly less than 1. So if we take this value and subtract 1 from it, we get a 0 from the left. So 2 divided by 0 from the left, this is negative infinity. And as we approach 1 from the right, we get a value of 2 divided by 0 from the right, which is positive infinity. So now let us move on to the horizontal asymptotes. So let's see how the graph behaves as we go to infinity. So as we go to positive infinity, the limit of 2x squared divided by x squared minus 1 as x approaches infinity. So what happens now is we can plug in as usual. We will get in the numerator infinity and in the denominator as well infinity. So what this means is that we can now use L'Hopital's rule. So we can take the derivative of the numerator, which will give us 4x, and the derivative of the denominator, which will give us 2x. And now again, let us see what we get if we plug in. So this will give us infinity over infinity again. We can, of course, use L'Hopital's rule, but we can also simplify. So we can just cancel the x from the numerator and the denominator. This will give us the limit of 4 over 2, which is 2. As x approaches infinity, 2 is a constant, so the answer is 2. Now let's do the same thing as x approaches negative infinity. Again, if we plug in, we will get infinity over infinity. So we can use L'Hopital's rule. You don't have to use L'Hopital's rule. So in fact, let's try another method and see that this still works. So let's try what we learned about before. So if we have infinity over infinity, we can factor the largest term. So x squared, we take it out, we are left with a 2, and at the denominator we take x squared out. We are left with a 1 minus 1 over x squared. So then we cancel the x squared and the x squared. This leaves us with the limit of 2 divided by 1 minus 1 over x squared. And so if we plug in, we get 2 divided by 1 minus 0, because 1 divided by x squared, so 1 divided by infinity, this approaches 0. So 2 divided by 1 minus 0 is 2, and this is our answer. So this means that we have a horizontal asymptote at y equals to 2. So now we have seen the asymptotes. Let us go and look what we're supposed to do next. We're supposed to find the first derivative, which is already given, and find when the graph increases, decreases, any critical points, minimum, local minimum, maximum. So let's do that. So this is step 4. Our first derivative was given to us. It is -4x divided by x squared minus 1 all squared. So let us find when the numerator is 0 and when the denominator is 0. So negative 4x equals to 0 when x equals to 0. X squared minus 1 all squared equals to 0. So x minus 1 times x plus 1, all of that squared equals to 0. So x minus 1 squared times x plus 1 squared equals to 0. So x minus 1 equals to 0, or x plus 1 equals to 0, x equals to 1, and x equals to negative 1. So these are the points we will put in our sign table. So I just drew the sign table. Let us try to fill it. So negative 4x is 0 when x equals to 0. And we can see that it has a negative sign. So even if, let's say, even if if x is greater than 0, then it will still be negative up here and positive down here. Now x minus 1 all squared is, we have a squared, so it's always increasing. Same for x plus 1 all squared, it's always increasing. So the first derivative is positive, positive, negative, negative. So it's increasing, increasing, decreasing, decreasing. Uh, we can write this as an interval if you want, or if you are ever asked. So this is negative infinity till negative 1, union negative 1 till 0. This is the interval when it's increasing, and it's decreasing over 0 till 1, union 1 till infinity. So you might notice that here it's increasing, and then it's decreasing, which shows that we have a maximum at x equals to 0. So we can write local maximum at x equals to 0, and this is we already found the coordinates to be 0, 0. And if you are ever specifically asked for the critical points, we said that the critical points are the points when the derivative is 0 or does not exist, as long as these points are in the domain. So let's see which of these points would be critical points. So x equals to 1 and negative 1 is not in the domain, but x equals to 0 is in the domain, so it is a critical point, and the coordinates are 0, 0. This is a critical point, which is also our local maximum. Moving on, we'll look at the second derivative, which is 12x squared plus 4 divided by x squared minus 1 all cubed. And of course, we can simplify the denominator to become x minus 1 all cubed times x plus 1 all cubed. So in order to proceed to draw the sign table to find the concavity, let us first solve each term equal to 0. So 12x squared plus 4 equals to 0, x minus 1 all cubed equals to 0, and x plus 1 all cubed equals to 0. So let's start with 12x squared plus 4 equals to 0. Notice that if we solve 12x squared equals to negative 4, then x squared equals to negative 1 over 3. This can never is never true, so 12x squared plus 4 cannot be 0. Now x minus 1 all cubed is 0, so x minus 1 equals to 0, so x equals to 1. X plus 1 all cubed is 0, so x plus 1 equals to 0, so x equals to negative 1. And now let's proceed to the sign table. So as I said, the term 12x squared plus 4 is always positive. X minus 1 all cubed is negative, negative, and then positive. X plus 1 all cubed, it's negative, positive, positive. Again, if you couldn't get it quickly, just plug in any number inside these intervals. Now the second derivative is therefore positive, negative, positive. So upward concavity, downward concavity, and then upward concavity. Notice that the concavity changes from upward to downward and then from downward to upward. So usually we would say that we have inflection points at negative 1 and 1. However, just a reminder that for these points to be inflection points, they have to be part of the domain. Are negative 1 and 1 in our domain? No, they are not. Therefore, they are not inflection points. So now we have reached our last step, which is sketching the curve. So first of all, of course, draw the x and the y axes. Next is sketch dotted lines for the asymptotes. So we have an asymptote at x equals to 1 and at x equals to negative 1. And we have a horizontal asymptote at y equals to 2. Now we want to know let's start with how the graph behaves from negative infinity till negative 1. So let's look at our first sine table. From negative infinity till negative 1, the graph is increasing, and it has an upward concavity. So in this upward concavity, we notice that this part is decreasing, which we don't want. We want the increasing part. So the graph will look something like this. Let's go and start sketching. So maybe something like this. Now let's see how the graph behaves from negative 1 till uh, to 0 and from 0 till 1. So from negative 1 till 0, the graph is increasing. From 0 till 1, it's decreasing. So this works well with our downward concavity, so it's increasing and then decreasing. And note that the point 0, 0 is a point on our graph because this is our critical point. And we also said it is a local maximum. So if it's a maximum, will have something like this right here. So I will continue graphing with purple. So maybe it will look something like this. And let's look how the graph behaves from 1 till infinity. So it is decreasing and it has upward concavity, so this part of the concave. So it will possibly look something like this. Now let's check if there's any information we did not use. So let's go back to where we started this exercise. So the domain does not include -1 or 1. Let's see if let's verify this. -1 or 1 are not part of the domain, so that's perfect. Now let's continue. We did the x-intercepts. We already put the point 0, 0, the x and the y-intercept, so that's good. Now, as we approach -1 from the left, the graph approaches infinity. And as we approach -1 from the right, the graph approaches negative infinity. So as we approach -1 from the left, the graph approaches infinity. And as we approach -1 from the right, the graph approaches negative infinity. Now let's continue. As we approach 1 from the left, the graph approaches negative infinity, and as we approach 1 from the right, the graph approaches infinity. So let's see if this is correct. So as we approach 1 from the left, the graph approaches negative infinity. As we approach 1 from the right, the graph approaches infinity. So far so good. Let's continue with the horizontal asymptote. So as the graph approaches positive infinity and negative infinity, it approaches 2, which is clear here. So as we approach positive infinity and negative infinity, we are approaching 2. Now let's see what else. And then we found the critical points, our local maximum to be 0, 0, and both sine tables, which we have already used. So we have verified that everything we found is aligned with what we drew. So this is how the graph would look like.